Thank you, Professor Cook, for your introduction. Hello, my name is Manuel Caracora Rios. I am a student in the few-body reaction group at the NSEL, and I'm going to talk about how we have used Bayesian methods to explore experimental conditions that reduce uncertainties in the optical model. I will be building on last Tuesday's talk by Dr. Amy Lowell, but I will briefly go over some of the basics. Um, As we know, a full many-body microscopic approach is currently not possible for intermediate and heavy nuclei. For this reason, we use few-body methods that require as inputs nucleus-nucleus optical potentials. These potentials are effective interactions that describe the many-body scattering problem. As Amy stated last Tuesday, our group has been looking into quantifying the uncertainties coming from the optical potential. So what are these optical potentials? These optical potentials have a Wood-Saxon shape and a derivative of Wood-Saxon shape, as well as a Coulomb function. Wood-Saxon potentials are characterized by three terms: depth, radius, and diffuseness. In our work, we fit optical phenomenological potentials to experimental data. To fit these potentials, we usually consider 9 parameters. The real volume with the depth, radius, and diffuseness, imaginary volume with depth, radius, and diffuseness, and the imaginary surface with the depth, radius, and diffuseness. We keep the spin orbit and Coulomb interactions constant. So just a reminder of last Tuesday's talk by Amy. In this work, we will be making use of Bayes' theorem, which states that our posterior distribution is equal to our prior times the likelihood divided by the evidence. The prior is what we know before seeing the data. In our case, we use white Gaussians. Our likelihood is how well the model describes the data. It is a normal standard distribution in our case. We use a standard chi-square definition as well. Our posterior distributions are obtained through a Markov chain Monte Carlo sampling and Metropolis Hastings condition. And our 95% confidence intervals for fitted and predicted data are defined by the smallest interval, where the integral over the posteriors is 0.95. So in other words, we define 95% confidence over the center of the densest regions of our posteriors. So what is the motivation of the work that I'm going to talk about today? It is that when my group started doing these Bayesian analysis that Amy talked about last Tuesday, we noticed that the uncertainties from the optical potential were larger than what we previously thought. In some cases, such as this lead 208 proton elastic scattering at 61 MeV, they can be as large as 100%. So we have here the 95% confidence bands from our Bayesian calculations and the corresponding error plot, where the error plot is simply the width of the band divided by the mean. So these uncertainties are clearly too large for physicists to extract useful information. And we started to think about ways to reduce the optical potential uncertainties with methods that are applicable to a large range of energies and elements across the nuclear chart. And so in this work, we tested 4 methods using Bayesian statistics to see if they would help. We looked at angular coverage, which is the number of data points in a differential cross-section dataset, and the region in which the points are located. We looked at including nearby beam energies in the fit. We looked at the effects of the experimental error on the parametric uncertainties. And finally, we also included the total reaction cross-section in the fit. So the first issue we ran into during this work was the availability of experimental data. To get around this issue, we generated mock data from a global optical potential, which is useful for 3 reasons. First, we can manipulate the experimental conditions. We are not restricted by the availability of experimental data. Uh, and it eliminates the model uncertainties and allows us to focus on the parametric uncertainties, which is what we're interested in. So mock data was generated using Conning de la Roche global parametrization. And we generated data for these reactions here. And so we generated a differential cross-section, a total reaction cross-section, and a polarization uh, data set for these energies. And to test the nearby energy principles, we also generated one at these energies. And so this data includes angles from 5 degrees to 160. And we selected the number of points to have between 6 and 12 data points per peak. We assigned a 10% so-called experimental error to keep to make this a realistic data set. So here, for example, I have a 48 calcium proton elastic scattering at 12 MeV data set that we use, and a 208 lead neutron data set at 30 MeV. So as I mentioned before, our Bayesian fitting, we will use 9 optical model parameters. Uh, we use wide Gaussian priors with a width of 100% around the Beckettian and Greenwich global optical parametrization. The data being fitted is mock data generated from Conning de la Roche. And so we pulled 1600 parameter sets with our Markov chain Monte Carlo sampling routine here. And here I have an example of a posterior distribution from our Bayesian fitting of calcium 48 at 21 MeV. So here, for example, I have the real volume term, the depth, radius, and diffuseness. The imaginary surface term are depth, radius, and diffuseness, and the imaginary volume term, depth, radius, and diffuseness. So we can see that our posteriors are not Gaussian, and we have more than one peak. So for example, here. A quick note, from now on, unless I explicitly state experimental data, I will refer to this mock data as simply data. So from our posterior distributions of optical parameters that we just saw, we can actually propagate our uncertainties to the DP transfer reaction using adiabatic wave approximation method, which was discussed by Amy on last Tuesday and includes the Durham breakup channel. Our inputs will be our posterior parameter sets. And it is for this reason that we chose elastic scattering energies to match the incoming and the outgoing channels. So for example, the lead 208 at 61 dp transfer, right here, we have chosen the incoming channels to be 30 MeV and for the neutron and the proton, and the outgoing channel for the proton to be at 61 MeV. And so this allows us to propagate the uncertainties coming from our Bayesian fitting to the single nucleon transfer. So now we get to the results of the 4 tests or methods that I mentioned. First, we will look at the angular thinning. So from our mock data, we generated a full data set. And we will test the effects of removing the backward angles of this data set. So the backward angles we defined as all angles above 100 degrees. And we will also test what happens if we reduce the number of data points by half. We fitted these 3 data sets and compared the results. So for example, here I have my full data set in the black dots and my reduced data set in red squares. And then we would use these as inputs for our fitting. So here are results for the 208 lead neutron scattering at 30 MeV. These are the 95% confidence bands and the error plot. Blue is using the entire data set. Orange is the data set with all angles above 100 degrees dropped. And so this is what we call forward. And green is the reduced data set where we have taken every other angle of the full data set, as we see here. Uh, we see that there's not much difference between the uh, blue and the orange. So there's not much difference, sorry, the blue and the green. And so we can tell that there's not much difference between the full and the reduced data sets. And the effects of just keeping the forward angles are noticeable only at the backward angles right here, which is what we expected if we drop those points. Um, So here are the rest of our results for the lead and their propagation to the transfer. We have here the incoming 208 lead neutron at 30 MeV, the incoming 208 proton lattice scattering at 30 MeV, and the outgoing proton channel. And here's the transfer. Sorry, oops. And here's the transfer. We see that the trends are basically the same. The full and reduced data sets are almost identical. So we see no penalty for reducing the number of data points. And the forward always gives more uncertainty in the backward angles. However, in the transfer, keeping only the forward angles seem to do a little better in the first 10 degrees. And so we see here the orange. And this highlights the nonlinearity of the problem when we propagate these uncertainties. And the fact that the full and reduced data set give very similar results can be attributed to the fact that the angular distributions are correlated. So a data set that captures the diffraction pattern is enough to give the information we need. And no further information, after we get to a certain point, no further information is gained by continuously adding more points. So for the calcium cases, we saw the same results. So now we will look at adding the nearby beam energies to the fit. So there are two ways we thought of doing this. The first one is done sequentially, which means we use the posteriors from the fit of the nearby energy as priors to the main energy we want to fit. Uh, the second is to include the nearby energy as a second data set in the fitting. As an example, I have the data for the 208 lead proton elastic scattering at 61 and 65 MeV. So the black dots correspond to the 61 MeV, and the red dots correspond to the 65 MeV. And now we see the results for the 208 lead proton elastic scattering at 61 MeV that we obtained from these two data sets. So this is the 95% confidence band and the error plot once again. In the plot, blue is a single data set for just place here for comparison. Orange is a sequential fitting of the data set, as I explained. And green is the simultaneous fitting. And we can see that although the sequential and the single data set are almost identical, we see a very large reduction in the uncertainty for the simultaneous multiple green fitting. And so we see that by including the second data set in the fitting process in the chi-square definition, we reduce the uncertainties in cases for up to 50%. So we can see here that the green is much lower than the other two. And this corresponds to the reduction in the uncertainty in the width of the band. We see that the other lead cases show a similar trend. We have the incoming channels, once again, 208 lead neutron at 30 MeV and 208 proton at 30 MeV, and the outgoing channels 208 proton at 61 MeV. And we see, and here's the transfer course, and we see that when fitting elastic scattering, the multiple or simultaneous fit, the green in these plots, always does better. And this lower uncertainty in all of the cases actually gets propagated to the transfer. And so now we will look at the results for the calcium. Uh, for the calcium cases, we see a similar trend. The sequential and single data 95% confidence bands are very similar in the reduction of their uncertainty, and the multiple or simultaneous fit has a much lower uncertainty. Sorry, not much lower, but it has a slower uncertainty. And we see that the uncertainty reduction is actually more modest than in the lead 208 cases, where we have reductions uncertainty by almost 50%. And from our analysis, we found two reasons why this might be the case. The first one is the energy regime. For higher energies, the second data set makes more of a difference, and we tested this by testing a case with high energy calcium. And the second thing that's impacting this more modest uncertainty is the percent difference in the energy of the nearby data. So, for example, for the lead, I showed a nearby data set. So for the outgoing channel, it was 61 MeV, and the nearby data was 65 MeV, which corresponds to a percent difference in energy of about 7%. For the calcium, we looked at 12 MeV, and the nearby data, for example, for this neutron incoming channel, it was 12 MeV, and the nearby data was 14 MeV. So this is more around 15 to 16%. And so this plays a factor. From these results, we can conclude that adding sequentially a second data set does not reduce the uncertainty. However, adding the data simultaneously in the fit and the definition of the chi-square significantly reduces the uncertainty, especially if the nearby energy is less than 10% away. So now we will look at the effects of the assigned error bar. Um, so when we generated our data set, we assigned a 10% experimental error, or not experimental, we assigned a 10% error to make this a more realistic and be able to define our fit. And so we wish to see how increasing or decreasing our 10% assigned error changes our parametric uncertainties. To do this, we will average the percent uncertainty at each angle of the error plot. So for example, for this 208 lead neutron case at 30 MeV and 10% assigned error, we will average the 95% confidence band error plot, so over all the angles, and then call this number epsilon 10. And so by taking the ratio of these averages over the different assigned errors that we will introduce 5%, 10%, and 20%. We can see how much the parametric uncertainty is reduced when we decrease the assigned error. We see that when the assigned error decreases, with the parametric uncertainty is also reduced. We can see this at this table. Uh, However, decreasing the assigned error by a factor of 2 does not decrease the uncertainty by that same level. And this stresses the nonlinearity of the problem. So for example, reducing the assigned error reduces the error by 1.39 in this case, and it could also reduce it by 1.94. And similarly, we can see that the 1.19 right below it for the outgoing channel. So now we will look at the results of including the reaction cross-section in the fit. Similarly to how we included the second energy, we will do it in the fitting process. Blue is a single data set of elastic differential cross-section placed here for comparison. And orange is the simultaneous fitting of the elastic differential cross-section and the total reaction cross-section. And it has been argued that including the total reaction cross-section might include some extra information to the fitting. The case shown here is the 48 calcium at 21 MeV, the 95% confidence band, and the error plot. And we see that adding the total reaction cross-section to the differential cross-section in the fitting process reduces the parametric uncertainty in some areas, but it is a modest improvement. Um, Before going on to the next slide to see the rest of the results, I wanted to point out there's actually a second data set of included here in this plot, and this is actually real experimental data. Uh, the, these purple stars, so you can see right here. And I placed here for the purpose of just seeing, so there was no fit done to these. It was just for the simple purpose of seeing how our mock data might compare to the real experimental data. And actually we see that even though we didn't fit this at all, most of the real data falls inside the bands. Um, so here we have all of the calcium 48 cases, the incoming channel at neutron at 12 MeV, proton at 12 MeV, and the outgoing channel proton at 21 MeV, and the transfer. Overall, we see the same trend for these results, some improvement in specific areas um, and regions. And for example, for the transfer, we saw that it does better below 20 degrees. And similarly, we have here all of the 208 lead cases, the incoming channels, once again, and the outgoing channel and the transfer. Uh, Actually, we do see a decrease in the uncertainty for the transfer here, even though we do not see a decrease in the uncertainty on the elastic, which again just goes to show how nonlinear the effects of propagating these uncertainties are. And we have been looking, so far we've been looking at how adding the reaction cross-section to the elastic differential cross-section constrains the 95% angular distributions. We can also do the same thing for predicting the reaction cross-section. And so here we have deviation intervals for the total reaction cross-section. And so this is deviation intervals for the total reaction cross-section obtained by fitting the reaction cross-section and the elastic. And this is the actual data point from our mock data. And we see that it always falls, the mock data point always falls inside the interval we're fitting, which is good. So we added the total reaction cross-section, and we just saw some very mild improvement. And so I wanted to see if adding polarization data to the fit somehow helped this situation. I did a simultaneous fit of differential cross-section with polarization, and I did another simultaneous fit of differential cross-section, polarization, and reaction cross-section. So I actually include all three observables here. So in the plots, blue is a single data set of differential cross-section placed here for comparison. Orange is a combination of differential cross-section with polarization. And finally, green is differential cross-section, polarization, and total reaction cross-section. So I have this one case here just to show the 208 lead neutron at 30 MeV. And we see that adding depolarization to the differential cross-section reduces the uncertainty. Adding the total reaction cross-section to the other two does not make much of a difference here. So the difference between the orange here and the green is very minimal. So it seems like the reaction cross-section does not add anything new once you already have added the differential and the polarization. So just as we saw previously, the total reaction cross-section, we can also do our Bayesian calculations to reduce the uncertainty in depolarization and look at depolarization observable. So here I have the 95% confidence bands for the polarization. But notice now that blue is no longer a single differential data set, but a polarization data set. So I follow blue always to be the natural observable. Uh, Overall, we see the same trend as for the differential cross-section confidence band. Adding the differential cross-section and polarization in a fit gives an improvement in the uncertainty. Adding the total reaction cross-section once again to the other two gives about the same, and we see that the orange and green bands are almost identical. And so we also conclude that adding the elastic observables to the fitting can only offer so much information, right? And I will talk a little bit more about this later. So um, I wanted to talk about sort of where this work fits, right? Because I am presenting some methods, and I wanted to talk about what was my motivation and our thought process as a group. So an experiment begins with the planning. Then it continues with the execution of the experiment itself, and it finishes in the interpretation of the data. Uncertainty quantification efforts can be used in the interpretation of the experiment. However, they can also be used in this sort of feedback loop that I have here. And so this work that I'm doing, falls into the Bayesian experimental design. And our goal is to develop methodology that can be of use during the planning of the experiment, and that will later on facilitate the or increase the precision of the interpretation. So I just wanted to give some context. Um, and now we go on to the outlook of what we are doing in uncertainty quantification. So I mentioned before that even by including all three observables, differential cross-section, reaction cross-section, and polarization, we somehow can only reduce the uncertainty to a certain point. And so our next goal is to diversify the data further to continue reducing the uncertainties. And this means including inelastic observables such as charge exchange. And we hope that this will contain other type of information than what can be obtained from elastic scattering. And also another venue of the investigation for our group is model comparison and nested models and model error. So for example, in the optical potentials that we showed, we might want to ask what happens if we remove the imaginary volume term. And so we will get a nested model. And so this range of uncertainty quantification, we're looking into the Bayesian evidence, which if you recall is simply the denominator in Bayes' theorem. And the Bayesian evidence gives a perfect way of doing these comparisons because that's what it does. Um, And well, the only problem is that deviation evidence can be quite difficult to calculate numerically, especially since our parameters are not Gaussian. And so in the immediate future, or in the more immediate future, we are currently finishing some work where we apply the same methodology that we used here, but to real experimental data. And we are also working in adding inelastic observables to the fit. So the conclusions of the work I've done. So we use Bayesian statistics to explore experimental conditions that can help reduce uncertainties. Our methods should be applicable to many energies and elements across the nuclear chart. And so we can draw the four conclusions based on the four methods. So once a diffraction pattern can be discerned, additional data points do not add new information as the angles are correlated. And also keeping the forward angles increases the uncertainty in the backward angles in all cases, which is what we saw and sort of expected. Um, Adding a second data set at a nearby energy simultaneously in the fit can help reduce the uncertainty up to 50%. To see this large reduction of the uncertainty, the nearby energy must be within 10% of the energy of interest. And we also saw that adding a second data set and a nearby energy sequentially actually does not help reduce the parametric uncertainty. Decreasing the experimental error bar, or the assigned experimental error bar, does help decrease the parametric uncertainty. But the gain is not directly proportional and varies with each reaction, as we saw in the table. And finally, a reduction of the parametric uncertainty can be obtained by fitting simultaneously the differential cross-section and the polarization. And adding the total reaction cross-section does add a constraint, but in a smaller magnitude than the other two observables studied. So before I finish, I would like to thank my collaborators, Garrett King, Dr. Amy Lovell, and Professor Filomena Nunes. And I would like to thank the Few Body Reactions Group at MSU and Leo Nevcourt for many helpful discussions, as well as ICER and HPCC for computational resources, and National Science Foundation for funding this work.